In this video, we want to look at how to calculate the value of the equilibrium constant if we're given the equilibrium concentrations for an equilibrium reaction. As you'll quickly learn, anytime you're dealing with an equilibrium system, probably the first thing you want to do is to write the equilibrium constant expression based on the coefficients in the balanced chemical equation. In this particular problem, since all of the equilibrium concentrations we're given are in concentration and molarity, then we'll go ahead and calculate the equilibrium constant with a subscript c, or the k sub c value. So the equilibrium constant expression using molar concentrations would be the concentration of HI raised to the second power, because we have a coefficient of 2 in front of HI, divided by the concentration of H2 multiplied by the concentration of I2. When we have this equilibrium constant expression, it's important to remember that all of these concentrations have to use the equilibrium concentrations for the problem. But in this particular problem, it specifies that all of these concentrations are already given to us at the equilibrium values. So what we have to do now is we have to read the problem and then fill in the equilibrium concentration values that are given to us in the problem into the equilibrium constant expression. Since these are given to us, we see that the concentration of the hydrogen iodide is 0.78, so that goes on top in the numerator and we'll square that value. And then in the denominator, we'll have 0.11 molar for hydrogen and 0.11 molar for the iodine gas. When we plug in these values into our calculator, remembering to square the numerator, we find that the equilibrium constant expression K sub C at this temperature is 5.0 times 10 to the first. And as we've mentioned when we began talking about equilibrium constants, these will just be numeric values without units, because equilibrium constants are unitless quantities. Let's look at another example. But in this problem, we see that what the information given to us is a little bit different. It tells us that the initial concentration of methane gas is 0.115 molar, and it's important to realize that this is an initial value. However, it does tell us that at equilibrium, the concentration of the C2H2 is 0.035 molar. Now, what this means is that we're going to have to make some assumptions, and we're also going to have to devise a method for determining the initial and the equilibrium values. The tool chemists use to tabulate initial and equilibrium values is called an ICE table. And that ICE, ICE, stands for initial, change, and equilibrium values of the concentrations of all of the reactants and products. In order to create the ICE table, we'll use the given chemical equation, and we'll put 3 rows and a heading at each row. The first row we'll use an I for initial concentrations, a C for the change in the concentration, and the capital E for the equilibrium concentrations. Once we've created the ICE table, we can add the known values that are given to us in the problem to help us see where we're starting. In this case, we know what the initial concentration of the methane is, and we also know where the equilibrium concentration of the C2H2 is going to be. So let's fill those in the table into the appropriate places. So now we've put 0.115 in the initial row for the methane, and we've put 0.035 in the equilibrium row for the C2H2. Now there are also some assumptions we can make. Since it says that initially we only knew the concentration of methane, we can make the assumption that the reaction has not started yet, and so the initial concentrations of C2H2 and H2 are going to be 0. What this means is that if the product concentrations are not given to us initially, we can assume that there's 0 concentration for the products initially, unless something is specified otherwise in the given problem. The fourth thing we'll want to do is for any reactants or products where we have both an initial and an equilibrium value, we can use that information to calculate the change value. Now in this case, we knew that we had 0 C2H2 at the beginning, but at equilibrium we had 0.035 molar. So how much did that change by? That would be the equilibrium minus the initial, which is 0.035 would be the change value. And that would be a positive value because as a product, that concentration increased. Once we know one of the values for the change for either the reactants or products, from that known value, we can use mole ratios from the balanced chemical equation to find the other change values. Now it's important to remember that the only place we're going to use mole ratios is only for values in the change row of the ICE table. In this case, since we know that the C2H2 changed by 0.035, and there's a 3-to-1 ratio between hydrogen and C2H2, then the hydrogen must have changed by 3 times the amount that the C2H did change. In other words, the hydrogen increased by 0.105 molarity. On the other hand, the mole ratio between the C2H2 and the CH4 is 1 to 2. So that tells us that the CH4 would have decreased by 2 times 0.035. And also, since the CH4 is a reactant, that means its concentration must be decreasing, so we put a negative sign in front of the 0.070 molarity change. Now that we have initial and change values for the CH4 and the H2, we can use those remaining initial and change values to calculate the equilibrium values for the CH4 and the hydrogen. For the methane, 0.115 minus 0.070 gives us an equilibrium concentration of 0.045 molar for the methane. For the hydrogen, since it's a reactant, the initial concentration of 0 plus a change of 0.105 tells us that at equilibrium we have a concentration of 0.105 molar for the hydrogen. Now that we've tabulated all of our equilibrium concentrations, we can now write the equilibrium constant expression based on the stoichiometry or the coefficients in the balanced equation. In this case, again, we put the products on top, so we have the concentration of C2H2 to the first power multiplied by the concentration of H2 cubed, since we have a coefficient of 3 in front of the H2. That will be divided by the concentration of methane, CH4, which will be squared because we have a coefficient of 2 in front of the methane. The last thing we have to do now is we have to fill in the values, the equilibrium values that we just solved for, and then we'll use those equilibrium values to calculate the value of the equilibrium constant. And when we plug in those values, and we're careful to make sure we cube the concentration of the H2, and we square the concentration of the CH4, we find that the value of the equilibrium constant for this equation is 0.020, and again, that is a unitless quantity.